Share my screen. Okay, let me know if you're not able to see anything on your screen. All right, the next example will be more application, a real life scenario. So what we have here is that we have a construction worker. Let's say you look at on your screen, there's a photo there. So this there's a construction happening, and then somebody dig a channel and then to feed the cable and so on. So the question just illustrate a scenario where you have a worker work in a trench to install a water line, and the trench is having a dimension of 3 meter long, 1.5 meter wide, and 2.5 deep. So this one will give you the volume dimension. As a result of being near to an intersection, a carbon dioxide means that if you run an engine, the engine products is one of the engine combustion process will give you carbon dioxide. And carbon dioxide is a bit heavier than common air, so it will sink to the trench here. So if you're a worker, then you might have the risk of having the CO2 poisoning happening case lah. All right, then okay, then this CO2 will displace the air in the worker need to breathe. So we will assume that there is the volume that we have is confined with the 3 meter, 1.5 meter, and 2.5 meter. Okay, and in this case we assume there's no mixing happen. Okay, later as we study a bit deeper, we will look at mixing happening in the next session. Okay, so in this case there is no mixing between air and carbon dioxide. We need to look at two things. A, estimate the time rate change of depth of carbon dioxide in the trench, del H or del T in meter per minute at any instant. Second, calculate the time it will reach 1.7 meter. That will be approximate adult height. So we need to calculate the safety time so that the worker will need to complete the work within that particular time frame. If not, then there's a risk of CO2 poisoning case will happen. So how we solve? The first, we draw the area or the control volume that we have. So we are having a 1.5 meter height, 3 meter, 1.5 meter length, and the CO2 is flowing into the control volume in the case. So this is a H that we need to find. All right. The CO2 is flowing from above and start filling the volume. So since we are using a fixed non-deforming control volume, then you need to highlight in your sketch. If this one come out in your test, remember always go and highlight your control volume. Okay, sketch the control volume, just follow the outline of the object. Then you'll score 1 mark for the effort defining the control volume. As usual, we write the quantity equation. Integration of your control volume plus the integration of your control surface. Be careful on the volume and the velocity in the equation. And we are using continuity equation, so equals 0. We need to be careful because we are having two entity here, or we having an air and CO2 in both cases. So for the control volume, we need to consider air and CO2. For control surface, we need to consider air and CO2 also. As is fill in the volume here, the volume is changing, control surface also changing. So what you can write here is that you expand the equation above. This one to these two. One is for air, one is for CO2. Two set, one is for air, one is for CO2. Then you expand the control surface, the m dot, to two component also. One is CO2, one is positive. One is CO2, one is A. Why CO2 is negative? Why this one is positive? Because CO2 is going in, pump into the system, and in it will always give you negative sign. Air is filling up, so it will give you a positive. Okay, to give you a positive sign. So just take note on this. When you fill up something, the component for the control surface will give you negative, and the one that is the air inside the system will get you positive sign. Okay, next. Okay, we pull the equation that we derived just now to the screen. Okay, so this one is control volume. This one is the control surface, CV, CS. So for the first one is about air. Okay, the first pair, you focus on air because air must conserve, because air doesn't change in the system. All right, air must conserve. The rate of change of air is m dot. Right? So CO2 also, CO2 must conserve because CO2 go into the system also consistent. So CO2 also conserve. So m dot CO2 is rate of change of CO2 also change with the same with the m dot. Okay, there's no loss of air and there's no loss of CO2 inside the volume. So you continue to process the equation. First, for CO2, you have an integration of CO2 rho V minus m dot CO2 equals 0. You substitute the value that you known because what we have is the carbon dioxide flow rate. So CO2, you pull the density out because density is a constant value. How you find the volume dV is that V equal to H times width times length. So width, height we do not know. So we take as dH times WL, 3 times 1.5 here. And then you simplify the equation that you have. You have del H over del T because you put the del T inside here. Then you pull the negative m dot CO2 to right hand side, you get a positive value. Okay, the next you expand your equation for m dot. M dot equal to rho Q, okay, or rho AV. A times V equal to Q. Okay, you can memorize rho AV. So when you write rho AV in your answer, you still get marks for that. So the rest is just substitution and rearrangement of your equation. So rho CO2 both sides cancel. Rearrange, pull your Q CO2 is given in the question. If you look back at the question, you see here CO2 go into the change at 3 meter cube per minute. So this is your Q. Q is volume flow rate. Is your Q. So you substitute the Q value, move this one 4.5 to right hand side, divide. So you take 3 divided 4.5, you get 0.667 meter over minute. You get the change of your height. Change of your height because of the CO2. Next, once you have the change of height, rate of change of depth of oxygen, not oxygen, carbon dioxide already found already, 0.667. Next, we look at the the time to fill when the what is the time to reach your H equal to 1.7. Why this is important in health and occupation work policy? You need to avoid CO2 poisoning, so you need to calculate the height of an adult to avoid poisoning. So you need to calculate the time before you ask your staff come up from the trench there. So how you find? This is your, just now your dH over dt, the rate of the height is 0.667 meter over minute. So to reach 1.7 meter, you just use T, you just convert del over del T. You want to find your T, right? You pull your T to right hand side, pull your 0.6 to bottom to the right hand side, left hand side. Then you have the H divided by T. So T equal to 1.7 divided by 0.667 will be 2.55 minutes or 2 minutes 33 seconds. So your worker need to come out from the hole or from the volume, from the workspace, 2 minutes 33 minutes before your worker drown in the CO2. Okay, so in this case, so if you work in a confined space, it's very easy to have this scenario happen, right? You have a CO2 poisoning. If you have a small space, 3 meter by 1.5 is a very small space, right? All right. So this is how we solve. So next lecture we look at another equation. So at this moment we stop at this example. Let me stop the recording.